Our entire modern world rests on a single, silent foundation. That foundation is measurement. Without the ability to quantify distance, time, or mass, the laws of physics would remain mysteries, chemistry would be alchemy, and astronomy would be stargazing. This video is the story of how innovations in measurement built the foundations of modern science. You will gain a complete understanding of how humanity's quest to measure everything, from the width of a hand to the vibration of an atom, created the very possibility of knowledge itself. How did a block of metal in Paris nearly derail global trade? What invisible force was finally weighed inside a quiet room? The tools we invented did more than collect data. They reshaped our perception of reality. What ordinary object in your home do you think represents the greatest leap in human understanding? The story of science begins not in a laboratory, but in the mud. Picture a human ancestor standing at the edge of a river needing to cross. They look at a fallen tree. Is it long enough? Their mind makes a calculation, not with numbers, but with a physical memory. They recall the length of their own stride, the reach of their arm. They might even lay their own body down beside the log to compare. This was the very first act of measurement. It was born from a simple, urgent need to interact with the world in a predictable way. That person was using the only universal tool they always had with them, their own body. The width of a thumb became an inch. The length from elbow to fingertip became a cubit. The distance of a single step became a pace. These were intuitive, personal, and brilliantly practical. You did not need a manual or a ruler, you were the ruler. This system allowed for the first great leaps of civilization. Communities could now agree, more or less, on how to build a wall that was 20 cubits long. They could divide a field into plots based on how many paces it measured. Trade could move beyond simple barter, as you could describe a length of cloth or a depth of grain. This was the monumental shift, the dawn of quantitative thinking. The world was no longer just a collection of vague impressions, big, small, near, far. It could be broken down into comparable, communicable parts. That conceptual leap is arguably more important than any specific unit they invented. It planted the seed for all future science, the idea that reality could be taken apart, counted, and understood. But this beautiful, body-centric system carried a fundamental flaw within it. My foot is not the same as your foot. My pace changes if I am tired. The king's forearm, declared as the official cubit, was different from the farmer's. What happens when you try to build a temple with 100 workers, each using their own personal cubit? The walls would not meet, the columns would not line up. This inconsistency was the first great problem that measurement had to solve. The very tool that created society now threatened to limit its growth. The quest for a truth that existed outside of any single human body had begun. A temple built with 100 different cubits would collapse before it was finished. This was the undeniable truth that forced humanity to make a crucial choice. We had to agree on a single truth, a single standard that existed outside of ourselves. The solution emerged from the grandest projects imaginable, the pyramids of Egypt and the towering ziggurats of Mesopotamia. To stack stone upon stone with such breathtaking precision required more than strong backs. It demanded a shared language of length. The Egyptian royal cubit was born. This was not just any forearm's length, it was a specific measure, often carved from black granite or polished wood, representing the pharaoh's own dimension. It became the master key. Architects across the kingdom could receive copies of this master cubit, ensuring that every block cut in a quarry hundreds of miles away would still fit perfectly in the rising monument at Giza. This was the architectural revolution, the shift from personal guesswork to communal precision. Standardization made the impossible possible, but think about what this really meant. That block of stone was no longer just a heavy object. It was a unit of 6 cubits or 12, a piece of a grand mathematical puzzle. The workers were not just laborers, they were executing a physical equation. This new system of measurement did something profound. It turned collective human effort into a single, coordinated force. The legacy of this is not just in the stones that remain. It is in the very idea that for society to function on a large scale, we must all agree to measure the world in the same way. It embedded measurement into the authority of the state and the divine. The pharaoh's cubit was not just a tool, it was a symbol of cosmic order made tangible on earth. The ambition was no longer just to build a big tomb. It was to create permanence, to etch human will into the landscape using the immutable language of mathematics. And if we could impose such perfect order on the chaotic earth, where else could we look for this kind of harmony? The natural next step was to lift our eyes from the monuments we built to the one perfect clockwork we could see in the sky above. The perfect order of the pyramids pointed our ancestors' gaze upward to an even greater architecture. The sun rose and set with unwavering regularity. The moon cycled through its phases. Certain stars returned to the same position in the sky at the same time every year. This was not just beauty, it was a clock. The universe itself was keeping time, and humanity learned to read its face. From the plains of Babylon to the courts of China, ancient astronomers became the first master timekeepers. They spent generations watching, recording, and counting. They tracked the precise moment the sun reached its highest point in summer and its lowest in winter. They mapped the repetitive dance of planets against the backdrop of fixed stars. This monumental effort was not born from abstract curiosity. It was a matter of survival. Knowing when the Nile would flood, when to plant seeds, or when the monsoon rains would arrive meant the difference between feast and famine. The celestial clock told them when to act. To capture this cosmic rhythm, they invented the first true measuring tools of time. A simple stick placed upright in the ground called a gnomon cast a shadow that moved predictably throughout the day. This was the humble beginning of the sundial, a device that literally translated the sun's journey into a visible, earthly measurement. Later, the brilliant complexity of the astrolabe allowed navigators and astronomers to measure the angle of stars, telling them not only what time it was, but where on the planet they were. This was a revelation. Time and space were being linked for the first time through measurement. The profound outcome of all this watching was the calendar. By quantifying the solar year as roughly 365 days and dividing the day into smaller units like hours, humanity imposed a grid of predictability onto the flow of existence. Religious ceremonies could be scheduled, trade routes could be planned, and history itself could be recorded in a sequence everyone agreed upon. But the deeper scientific breakthrough was the realization it confirmed. The cosmos operated by rules. It was not a chaotic realm of gods acting on whims. It was a system that could be observed, predicted, and described with numbers. This faith in a predictable universe is the bedrock of all science. It gave us the courage to ask questions, expecting consistent answers. The measurement of time provided the essential tempo, the steady beat against which all other changes could be measured. It created the first laboratory, not made of walls but of centuries. And with this new, reliable sense of time in their minds and these tools in their hands, people began to look beyond their horizons, wondering what else in this vast, orderly world could be counted and mapped. But the sky was not the only place demanding precise numbers. Down here on the ground, another force was pushing measurement forward, the relentless drive of commerce. Imagine a merchant on the ancient Silk Road, his camels laden with silk from China and spices from India. He arrives at a bustling market in Persia. The local trader wants to buy a specific weight of cinnamon. How do they agree on what that weight is? If the merchant uses stones from his own village as weights, and the buyer uses stones from his, the potential for confusion or outright deception was enormous. A trade that should build connection could just as easily spark a bitter dispute. This was the daily reality across the expanding trade networks of the ancient world. Irregular weights and inconsistent volumes were more than an annoyance. They were a direct barrier to trust and therefore to economic growth. The solution emerged from the same principle that built the pyramids: standardization. Cultures around the world independently arrived at the same idea. They created official units of mass and volume, and they made those standards public. In Babylon, you had the mina. In Rome, it was the libra, the ancestor of our pound. These were not abstract numbers. They were physical objects. A master weight, often made of stone or metal, would be kept in a temple or the central marketplace under the watchful eyes of both priests and merchants. This block of bronze was the ultimate authority. Anyone could bring their own goods or their own scale weights to compare against this public truth. This simple act transformed commerce. It moved trade from a realm of personal trust, which could be broken, into a realm of verifiable fact, which could be witnessed. The tool that enabled this verification was the balance scale. Its elegance is profound. Place the official weight on one pan and your goods on the other. If the beam hangs level, the transaction is fair. The scale made justice visible. It introduced a powerful new concept into everyday life: empirical proof. You did not have to argue or take someone's word for it. You could demonstrate the truth for all to see. This commercial need for fairness and accuracy did something remarkable. It fostered a culture of verification, a mindset that demanded evidence before belief. The marketplace, with its haggling and its scales, became an unexpected training ground for scientific thinking. People grew accustomed to the idea that claims about the physical world, like the weight of a bag of grain, needed to be tested against an independent standard. This habit of mind, born from the practical need to prevent fraud, would become the very soul of the scientific method centuries later. So the pursuit of honest profit quietly laid the groundwork for a revolution. It taught humanity to question, to compare, and to demand proof. And once that skeptical, evidence-based mindset took root in the world of commerce, it was only a matter of time before someone turned that same rigorous gaze away from bags of spice and toward the fundamental substance of nature itself. That skeptical gaze from the marketplace found its ultimate target in nature itself. The European Renaissance did not just paint beautiful pictures, it built a new toolkit for seeing. This was a revolution of instruments, devices that acted as extensions of the human senses, allowing thinkers to probe the universe with questions instead of just wonder. The precision compass and the mariner's quadrant transformed the treacherous sea into a measurable grid. Sailors were no longer guessing their position by following coastlines. They were calculating it using angles to the stars. This new accuracy birthed modern cartography, turning vague, monster-filled edges of the map into precise coastlines and navigable oceans. The world suddenly became a place you could locate yourself within, down to a specific point. But the most dramatic extensions of sight looked inward and outward. The microscope revealed a teeming, chaotic universe in a single drop of water, a world of creatures living entire lives unseen. The telescope, turned toward the heavens, did something even more profound. It did not just bring the moon closer, it shattered an ancient cosmic order. When Galileo trained his spyglass on Jupiter, he saw 4 tiny points of light orbiting the giant planet, a miniature solar system in motion. This was visual, measurable proof that not everything revolved around the Earth. The tool provided evidence that dogma could not ignore. Yet, perhaps the most quietly transformative instrument of all was the pendulum clock. Pioneered by Christian Huygens, it harnessed the regular swing of a weight to tick away seconds with a reliability that sundials and water clocks never could. This gave science something it desperately needed, a precise way to measure short intervals of time. Now, change could be quantified not just in days or hours, but in heartbeats of a pendulum. This was the final piece. With reliable time, distance, and observation now possible, thinkers could stop merely describing nature and start experimenting upon it. Galileo could roll balls down inclined planes and time their descent with that steady tick, tick, tick. He was not just watching motion, he was interrogating it, forcing it to reveal its mathematical secrets under controlled, repeatable conditions. The result was not a philosophical speculation, but a law of falling bodies. This was the monumental shift. The Renaissance demonstrated that every leap in scientific understanding is first a leap in our ability to measure. Each new device, from the humble compass to the majestic telescope, did not just provide answers, it posed sharper, more daring questions. The instrumental revolution created a new kind of thinker, part philosopher and part engineer, armed with tools that made the invisible visible and the vague exact. This new philosophy demanded proof you could see, measure, and repeat. And once that standard was set, the search began for the one master measurement that could tie all of nature's forces together into a single, elegant system. The pendulum's steady tick created a new kind of room. Before the 17th century, philosophers pondered nature in libraries or under open skies, but to truly interrogate reality, you needed a space you could control. This was the birth of the laboratory. It was not just a room with tools, it was a sanctuary for measurement, designed to shut out the unpredictable world so a single, precise question could be asked. Inside these spaces, thinkers like Robert Boyle performed a new kind of magic. Using an air pump, a terrifyingly complex device of brass and leather, he could slowly suck the air out of a glass jar. Inside that jar, a candle's flame would sputter and die. A bell would become silent. He was not just watching nature, he was putting it in a cage and testing its limits. By meticulously measuring how the volume of a gas changed as he altered the pressure, he could derive a law, a predictable mathematical relationship. This was the revolutionary shift. The laboratory turned the grand questions of natural philosophy into a series of small, measurable, and repeatable steps. The scientific method was not a philosophy written in a book, it was the practical rhythm of this new workspace. Observe a phenomenon, form a hypothesis, a guess about the rule behind it. Design an experiment to test that guess by measuring the outcome. Then draw a conclusion based solely on what the numbers revealed. This entire process hinges on one capability: accurate measurement. Without a reliable way to quantify the pressure in Boyle's pump or the temperature of a flame, the experiment is just a spectacle. The data is what transformed a demonstration into a discovery. This institutionalization of measurement created a powerful feedback loop. A scientist, limited by the crudeness of their thermometer, would design a better one. That new, more sensitive instrument would then reveal subtle effects they had never noticed before, leading to a new hypothesis, which demanded an even more precise experiment. The laboratory became an engine for generating both better tools and deeper truths. It established a new authority, one based not on tradition or eloquent argument, but on reproducible results. If you doubted Boyle's law, you could build your own pump and measure it yourself. This was the true foundation of modern science, a communal enterprise built on a shared trust in measured evidence. Yet, a profound problem was emerging from this very success. Every laboratory, every nation was developing its own exquisite standards, its own perfect pound or flawless foot. The language of science was becoming a Tower of Babel, where a brilliant discovery made in London might be unverifiable in Paris because their inches and their pounds were subtly different. The quest for truth now demanded a new, even grander ambition, a universal language of measurement that belonged not to any king or country, but to the world itself. The very success of the laboratory created a crisis of communication. Science was speaking in 1,000 different tongues. A brilliant experiment performed in London with its precise inch could not be perfectly replicated in Paris with their slightly different paus. This was more than an inconvenience, it was a barrier to truth itself. Then came the chaos and the idealism of the French Revolution. In the ashes of the old monarchy, revolutionaries sought to rebuild society from first principles based on reason alone. And they realized that to create a rational world, you first needed a rational way to measure it. Out of this fervor came a breathtakingly ambitious idea. They would not base their new units on a king's foot or a farmer's stride. They would derive them from the earth itself. A team of scientists was commissioned to perform one of the greatest measuring feats in history. They would survey a meridian arc from Dunkirk to Barcelona, a painstaking trek across mountains and through political turmoil to calculate the distance from the North Pole to the equator. From this, they defined the meter as 1/10,000,000th of that quarter circumference. It was a unit born from the planet. To accompany it, they defined the kilogram as the mass of 1 liter of pure water at its densest point. This was the radical heart of the metric system. It declared that the true standards of measurement were not in a royal vault, but woven into the fabric of nature, waiting to be discovered by reason. The meter and the kilogram were more than tools, they were philosophical statements. They embodied a profound belief in a universe that was consistent, measurable, and accessible to all people everywhere. This was science as a democratic act. The political revolution had directly accelerated a scientific one, proving that a shift in ideology could unlock new ways of seeing the physical world. The practical impact was immense. For the first time, scientists across borders could share data with absolute confidence. An industrialist in Lyon could order a precision screw from a factory in Belgium, knowing it would fit perfectly. The metric system provided a universal grammar for progress. Its journey from a revolutionary decree scribbled in Paris to the foundational language of global trade and research is a testament to the power of a simple, elegant idea. It showed that when humanity agrees on a common framework for describing reality, collaboration and discovery flourish on an unprecedented scale. Yet, this beautiful system, rooted in the earth itself, soon revealed a subtle, ironic flaw. What happens when your perfect standard, based on nature, is itself imperfectly made? The quest for universality now demanded a pursuit of perfection so exacting it would redefine the meaning of precision. The meter was a perfect idea, but the physical object was a problem. The platinum bar crafted to embody its length, stored under glass in Paris, was not immune to the very world it was meant to measure. Over decades, microscopic scratches, the faintest wear, even the settling of the earth beneath the vault could, in theory, change it. Scientists now faced a paradoxical quest. They needed a standard so perfect it was beyond the reach of any physical artifact. This hunt for an immutable truth would lead them to probe the deepest nature of reality itself, beginning with something we all feel but could not yet truly see: heat. Heat was the ghost in the machine of the early scientific revolution. You could feel its presence, see its effects in a boiling kettle or a glowing forge, but what was it? For centuries, it was considered a fluid, a substance called caloric that flowed from hot objects to cold ones. To banish this ghost and understand it, you first had to give it a number. That was the challenge taken up by inventors across Europe. Galileo sketched a device called a thermoscope, a glass bulb that trapped air over water. As the air inside warmed and expanded, it pushed the water level down. It was a brilliant demonstration, but it was fickle, swayed by air pressure as much as by temperature. The breakthrough came when experimenters sealed the glass and replaced the air with a liquid, first wine spirits, then the brilliant, silvery mercury. These liquids expanded and contracted with a beautiful, predictable consistency when heated or cooled. But to turn this observation into a tool, you needed a scale, a shared language of hot and cold. Two names would define that language. Daniel Fahrenheit, a German instrument maker obsessed with precision, wanted to avoid negative numbers on his weather reports. He defined 0 as the temperature of a frigid brine solution, and 96 degrees, oddly, as the temperature of the human body. His scale gave us the precise, fine-grained measurements that would fuel engineering. Then came Anders Celsius, who proposed a more elegant, decimal-minded approach. He set 100 degrees as the freezing point of water and 0 as its boiling point, a scheme later flipped to the intuitive scale we use today. With these sealed glass tubes and their etched numbers, something magical happened. The subjective sensation of warmth, something you could only describe as hotter than before, was transformed. It became temperature, a quantifiable property of matter, as real and measurable as length or weight. You could now say with authority that the difference between a simmer and a rolling boil was exactly 20 degrees Celsius. This was not just an improvement, it was a new sense. Armed with this new sense, scientists could finally interrogate heat. They could measure exactly how much energy it took to melt a block of ice or boil a pot of water. These careful measurements revealed the laws of thermodynamics, the fundamental rules governing energy. The first law stated that energy could neither be created nor destroyed, only transformed. The second law introduced a profound and sobering concept, entropy, the inevitable tendency of useful energy to dissipate into disorder. But perhaps the most haunting idea to emerge from this new precision was the notion of absolute zero. By carefully measuring how gases contracted as they cooled, scientists extrapolated to a theoretical point where all molecular motion would cease, a temperature of negative 273.15 degrees Celsius. This was not just a number on a scale, it was a frontier, an absolute limit imposed by nature itself. The pursuit to measure ever lower temperatures, using ever more sensitive devices like gas thermometers and platinum-resistant sensors, became a driving force of discovery. It led to the liquefaction of gases, the discovery of superconductivity, and our modern understanding of quantum states. Each refinement in thermometry did more than give a better reading, it unlocked a deeper layer of physical truth. The mastery of temperature measurement did not stay in the laboratory. It powered the modern world. James Watt could not have perfected his steam engine without accurate thermometers to monitor the boiler. The entire science of metallurgy, which gave us steel skyscrapers and alloy engines, depends on controlling heat with exquisite precision. From the thermostat in your home to the global monitoring of climate change, our ability to quantify temperature shapes civilization. This story reveals a powerful pattern in the history of science. Precision in one domain, the simple act of assigning a reliable number to heat, sparks revolutions in another. It tamed energy, defined the limits of the possible, and showed that to understand the forces that shape our universe, we must first learn to measure them. And as we reached for the coldest cold, scientists were already turning their instruments toward the most elusive measurement of all, the invisible pull that governs the cosmos itself. Electricity was once a ghost in a glass jar. In the salons of 18th century Europe, a gentleman scientist would rub a rod of amber with silk, producing a faint crackle and a tiny, startling spark. It was a marvelous trick, a fleeting whisper of an invisible force. For science to claim this ghost, it needed to give it a number, to weigh it and count it. The first tool for this capture was the electroscope. A simple glass jar held a delicate metal rod with two thin gold leaves attached. When a charged object was brought near, the leaves would splay apart, repelled by the mysterious influence. It was a yes or no detector, a silent witness to the presence of charge, but it could not tell you how much. The ghost was still invisible. The breakthrough came with the refinement of this tool into the electrometer. Scientists like Lord Kelvin transformed it from a simple detector into an exquisitely sensitive measuring device. His quadrant electrometer used tiny, oppositely charged metal plates. The slightest electrical potential would cause a delicate needle, suspended by a quartz fiber thinner than a spider's silk, to twist. The degree of that twist, observed through a microscope, could be precisely calibrated. For the first time, the strength of an electrical force had a scale. This was the moment electricity stopped being a parlor trick and became a science. Now, researchers could perform experiments with numbers. Charles Augustin de Coulomb, using a sensitive torsion balance, could measure how the force between two charged spheres changed with distance. His law emerged from those careful measurements, a precise mathematical relationship stating the force weakened with the square of the distance. Georg Simon Ohm, by meticulously measuring current flowing through different lengths of wire, uncovered the simple, profound relationship between voltage, current, and resistance. Michael Faraday, probing the link between electricity and magnetism, could quantify the exact amount of current induced by a moving magnet. Each of these monumental laws, the very alphabet of electrical engineering, was written not in ink, but in data points recorded from an electrometer's quivering needle. This precise quantification changed everything. An engineer could now sit at a desk and design a circuit on paper, calculating the exact wire thickness and battery power needed, because every element obeyed a measurable law. The abstract force became a predictable, manageable tool. The generator, the motor, the electric light, none of these were possible without first mastering the measurement of volts and amps. This episode reveals a profound truth about scientific progress. The greatest leaps forward often come not from a sudden brilliant idea, but from a quiet, painstaking improvement in our tools of measurement. When we learn to quantify what was once only a qualitative wonder, we unlock the door to controlling it, to building with it, to weaving it into the fabric of civilization. And if we could measure the invisible push and pull of electricity, what about the most fundamental framework of all, the very stage upon which everything else plays out? The next measurement would have to capture space and time themselves, not as separate ideas, but as a single, interwoven entity. The ghost of electricity had been tamed by a quivering needle, but a far grander force remained unmeasured. How do you weigh the invisible pull that holds the universe together? By the late 18th century, Isaac Newton had described gravity with breathtaking mathematical elegance, but his universal law contained a ghost of its own, a mysterious constant, g. This number represented the strength of gravity itself, the fundamental handshake between any two pieces of matter in the cosmos. To find it, you would need to measure the unimaginably faint attraction between two ordinary objects in a room. Most scientists thought this was impossible, a force too weak to ever be detected by human hands. Then came Henry Cavendish, a man of immense wealth and profound shyness, who decided to build an instrument of impossible sensitivity. His creation was the torsion balance. Imagine a 6-foot wooden rod, suspended horizontally from its center by a thin metal wire. At each end of the rod, Cavendish hung a small, dense lead sphere. He then placed two massive, 300-pound lead balls in a separate wooden frame, which could be swung close to the small spheres. The entire apparatus was sealed inside a cramped, dark shed to shield it from stray air currents and even the warmth of his own body. His tool was not a machine of power, but one of silence and stillness, waiting to catch the faintest whisper of the cosmos. The principle was sublime in its simplicity. Gravity, that force which binds planets to stars, would exert a tiny pull between his large and small lead balls. This minuscule attraction would cause the horizontal rod to twist ever so slightly on its wire. Cavendish's genius was in how he measured that twist. He attached a small mirror to the wire, and by shining a beam of light onto it and watching the reflected spot move across a scale on the far wall, he could magnify the motion. The movement of a light spot, a fraction of an inch, told the story of a universal force. For months he watched, adjusted, and measured with monastic patience. The pull he was detecting was almost absurdly small, comparable to the weight of a single grain of sand, but it was there, consistent and measurable. From that delicate twist, Cavendish performed a monumental calculation. He did not just measure the constant, he effectively weighed the Earth itself. By knowing the force between his balls and their masses, he could deduce the mass of our entire planet. His result was staggeringly accurate, within 1% of the value we accept today. The philosophical impact was profound. Cavendish had done the unthinkable. He had brought the force that governs the orbits of galaxies down into a quiet shed and pinned a number to it. His experiment declared that the laws of nature were not just beautiful ideas, they were precise, quantifiable, and testable anywhere. The universe spoke a mathematical language, and with enough care we could learn to listen. This pursuit of the fundamental constants, like G, became the new frontier. It was a search for the immutable numbers woven into reality, the settings on the cosmic dial. Each constant represented a deep truth about how the universe was built, and measuring them became the highest calling of experimental science. Cavendish's legacy was a quiet revolution. He proved that the answers to the grandest questions often lie in the smallest, most carefully measured signals. And if we could weigh a planet from a dark shed, what other invisible threads connecting everything in existence might we yet learn to measure? Newton's quiet shed had weighed the Earth, but light remained a profound mystery. A century earlier, in a darkened Cambridge room, Isaac Newton performed a deceptively simple experiment. He allowed a thin beam of sunlight to pass through a triangular piece of glass, a prism. The beam did not merely bend, it exploded into a band of color, a miniature rainbow projected on his wall. This was more than a pretty effect. Newton realized he was witnessing the dissection of light itself. White light was not pure, but a mixture, and the prism was a tool that could separate it into its fundamental components by their unique degree of bending. In that moment, he was not just a physicist, he was creating an entirely new instrument for measurement. He was building a ruler for light. That ruler needed finer markings. The prism's rainbow was beautiful but blurry, its colors blending at the edges. The quest for precision demanded a better tool, and it arrived in an unlikely form, the diffraction grating. Imagine scratching thousands of perfectly parallel, microscopic lines onto a polished surface of glass or metal. When light hits this etched surface, it does not just reflect, it scatters. Each wavelength, each specific color of light, interferes with itself in a precise way, fanning out into an incredibly sharp spectrum. A high-quality grating could spread light into a spectrum so detailed it looked like a finely ruled musical staff, with dark and bright lines at exact positions. This was the breakthrough. Scientists could now measure the exact wavelength of any sliver of light with stunning accuracy, just by measuring the angle at which it emerged from the grating. This new power gave birth to an entirely new science, spectroscopy, the art of reading light's fingerprint. Every element in the universe, when heated until it glows, emits light at a unique set of wavelengths. Sodium burns with a harsh yellow, neon blazes with a fiery orange-red. Through a spectroscope, these colors resolve into a precise barcode of bright lines, an elemental signature as unique as a human fingerprint. The inverse is also true. When a cooler gas floats in front of a hot light source, it absorbs those same specific wavelengths, leaving dark lines in the spectrum. Armed with this new decoder ring, astronomers turned their telescopes toward the stars. The results were nothing short of revolutionary. By simply capturing the faint starlight and passing it through a spectroscope, they could now read the chemical composition of a star millions of light years away. They could measure its temperature by which lines were strongest. Most astonishingly, they could measure its motion. If a star was moving toward us, its light waves would be compressed, shifting its entire fingerprint toward the blue end of the spectrum. If it was moving away, the fingerprint would stretch toward the red. This Doppler shift, measurable with a grating, revealed the universe was not static but in dynamic, rushing motion. Spectroscopy transformed astronomy from a science of mapping positions, of plotting dots on a celestial sphere, into a science of physics. It proved that measurement could bridge the unimaginable gulf of space. We could now take the temperature of a star, weigh its elements, and clock its speed, all from a tiny packet of photons that had traveled across the cosmos to land on our mirror. The analysis of light became humanity's primary remote sensing tool, turning every star and galaxy into a broadcast station, sending out a coded message about its nature. If we could decode the light from the largest objects in the universe, the next logical step was to turn this same precise gaze toward the very smallest. The universe had just begun to whisper its secrets through light, but there was a far more elusive signal to capture. Deep within the atom, a hidden energy was leaking out. It was a force you could not see, taste, or feel, yet it could fog a photographic plate left in a drawer or make certain minerals glow in the dark. This was radioactivity, and for scientists at the dawn of the 20th century, it was a profound puzzle. How do you measure something that is completely invisible, yet powerful enough to pass straight through walls? The phenomenon was both fascinating and frightening, a natural process that seemed to violate the old rules of permanence, hinting at a universe built from unstable, energetic cores. To understand it, they needed a way to make the invisible not just visible but countable. The breakthrough arrived in a deceptively simple box. Hans Geiger, working with his student Walter Müller, created a device of elegant simplicity. A metal tube filled with a special gas had a thin wire running down its center. They applied a high voltage just below the level needed to cause a spark. When a single particle from a radioactive decay, like an alpha or beta particle, zipped through the tube, it would knock electrons off the gas atoms inside. Those freed electrons would then accelerate in the electric field, colliding with more atoms and starting a tiny, self-contained avalanche of charge. This microscopic cascade would register as a sudden, distinct pulse of current. The genius of their design was in its output. That pulse could be wired to a meter that jumped with each event, or, more famously, to a small speaker that produced a sharp, audible click. For the first time, the disintegration of an atomic nucleus, an event happening on a scale trillions of times smaller than a grain of sand, announced itself with a sound. That click was a revolution. It turned an abstract, terrifying force into something you could literally listen to and count. A researcher could hold a speck of uranium ore near the tube and hear a sporadic pop, pop, pop. Move it closer and the clicks would merge into a frantic, continuous crackle. This simple audio feedback was transformative. It democratized nuclear physics. You did not need a giant laboratory or a complex photographic setup. With a Geiger counter, any scientist, any student, could become an explorer of the atomic nucleus. They could now perform precise experiments. By counting clicks over time, they could measure a half-life, the statistical clock that governs how quickly a radioactive substance decays. They could trace the path of radioactive traces through a living plant or animal, illuminating biological processes that were once completely hidden. They could even measure dosage, understanding how much radiation was too much, turning a mysterious hazard into a managed risk. This act of quantification changed everything. What was once a mysterious and ominous power became a precise scientific tool. Those clicks led directly to life-saving innovations in medicine, from radiation therapy to medical imaging. They enabled the discovery of new elements and the mapping of the nuclear landscape. The Geiger counter did more than detect radiation. It tamed it by giving it a number. It proved that even the most elusive and potent forces of nature yield to the persistent human drive to measure. With this simple device, humanity learned to count the very heartbeat of the atom. And if we could count individual atomic events, the logical next step was to demand a clock so perfect, so unerring, that it could time the universe itself. The steady clicks of the Geiger counter were a countdown to a new definition of time. For millennia, we had measured seconds by the swing of a pendulum or the orbit of our planet, rhythms tied to the grand but imperfect mechanics of our world. To find a truly perfect beat, science had to listen deeper to the silent hum inside the atom itself. That hum is the vibration of an electron. In a cesium-133 atom, an electron orbiting the nucleus can exist in one of two very specific energy states. Think of it as a tiny switch that can only be flipped up or down with no position in between. The magic happens when you hit the atom with a microwave signal tuned to exactly the right frequency. At that perfect pitch, the electron will resonate, absorbing the energy and flipping from the lower state to the higher one. This is not a suggestion, it is a law of quantum mechanics. The atom is an exquisitely finicky tuning fork that will only sing one pure note. In the 1950s, scientists built a machine to listen for that song. An atomic clock heats cesium atoms into a vapor and shoots them down a long tube. As they fly, they are bathed in that carefully tuned microwave beam. A detector at the end counts how many atoms have had their electrons flipped. The engineers then constantly adjust the microwave frequency, searching for the exact point where the maximum number of atoms resonate. When they find it, they have locked onto nature's own metronome. That frequency, 9,192,631,770 cycles per second, is now the official definition of 1 second. This was a philosophical leap as profound as the metric system. We abandoned the cosmic clockwork of the heavens for the quantum heartbeat of matter. The precision is almost incomprehensible. The best modern atomic clocks, often using strontium atoms in lattices of laser light, are so stable they would not gain or lose a second over the entire age of the universe. This is not just laboratory bragging rights, it is the silent engine of your daily life. Every GPS satellite carries an atomic clock. The system works by timing how long a signal takes to travel from the satellite to your phone. Since those signals move at the speed of light, a timing error of just 1/1,000,000th of a second would translate to a positioning error of 300 meters. Your phone's map app is in essence a continuous conversation with these orbiting quantum timepieces. Global financial networks rely on them to timestamp transactions to the nanosecond. The internet itself is synchronized by these clocks. They even allow us to test Einstein's theory of relativity with stunning accuracy. According to his predictions, time itself runs slower in a stronger gravitational field. An atomic clock placed just a few centimeters lower on a lab bench, deeper in Earth's gravity well, will tick measurably slower than one higher up. We can now measure this warping of space-time not across galaxies, but on a tabletop. The atomic clock represents the ultimate triumph of the measuring impulse. It proves that to master the macroscopic world, we must first command the microscopic. Our modern infrastructure, from navigation to communication to fundamental physics, is built on the unwavering stability found in the quantum realm. And if we can use atoms to measure time with such breathtaking exactness, what about using them to create a map, a picture of the world at its most fundamental scale? The atomic clock listened to the universe's most precise heartbeat, but our eyes were still blind to its smallest building blocks. That changed in a laboratory in Zurich in 1981, with the invention of a device that did not just detect atoms, it touched them. The scanning tunneling microscope was a machine of profound simplicity and staggering implication. It worked on a principle that sounds like science fiction. A needle sharpened to a point just a single atom wide is brought incredibly close to a surface, but without actually touching it. At that vanishingly small gap, a quantum mechanical miracle occurs. Electrons can tunnel across the empty space, creating a tiny, measurable electrical current. This current is exquisitely sensitive to distance. If the needle passes over an atom on the surface, the gap shrinks by a fraction of a nanometer and the tunneling current surges. If it passes over a valley, the current drops. By scanning the needle back and forth, line by line, and constantly adjusting its height to keep the current steady, the machine builds a topographical map. What emerged on the computer screen was a revolution in human perception. For the first time, we could see the individual atoms that make up a crystal of silicon or a flake of graphite, not as blurry blobs in an electron microscope, but as crisp, three-dimensional spheres arranged in perfect, repeating lattices. It was like discovering that the smooth marble floor you have walked on your entire life is actually a mosaic of billions of perfectly cut stones. The abstract ball and stick models from chemistry textbooks were suddenly real, tangible landscapes you could navigate. The scanning tunneling microscope did more than see, it could feel and even push. By adjusting the voltage on the tip, researchers found they could nudge individual atoms across a surface. In a famous and breathtaking experiment, scientists at IBM used 35 xenon atoms to spell out their company's logo on a nickel crystal. They were no longer just observers of the atomic world, they had become its architects. This ability to measure and manipulate at the nanoscale transformed entire fields. In materials science, researchers could now directly observe defects in atomic structures that weakened metals or impurities that supercharged semiconductors. In chemistry, they could watch reactions unfold at the single molecule level, following the dance of bonds breaking and forming. The tool provided the ultimate empirical proof, a direct, quantifiable measurement of atomic reality. It turned the philosophical concept of the atom into a daily engineering reality. Our drive to measure the very small had reached its logical extreme, proving that to truly understand something, you must be able to map it, touch it, and count its fundamental pieces. If we can now chart the peaks and valleys of a single atom, it forces a staggering parallel. The same human impulse that meticulously mapped a grain of silicon now looks upward, driven to perform the same act of measurement on the grandest canvas imaginable. Mapping a single atom is a staggering act of precision, but it echoes a much older human ambition. For centuries, the greatest and most haunting question was simply, how far? How far away are those points of light? The answer could not be found with a single brilliant instrument. It required the construction of a cosmic distance ladder, a series of interlocking steps where each new measurement stood upon the shoulders of the last. The first rung is the most intuitive, a trick of perspective you can try yourself. Hold your thumb out at arm's length and close one eye, then the other. Your thumb appears to jump back and forth against the background. This is parallax, and astronomers use the same principle with the Earth's orbit. They observe a nearby star against the distant stellar background in January, and then again 6 months later in July, when the Earth is on the opposite side of the Sun. The star appears to shift its position by a tiny, almost imperceptible amount. That tiny angle, measured with exquisite care, allows for a straightforward trigonometric calculation, giving us a direct geometric distance. It is the most fundamental and reliable method we have, but it only works for stars relatively close to us within a few thousand light-years. Beyond that, the parallax shift becomes smaller than our instruments can detect. To reach further, we need a new kind of rung, one based not on geometry but on recognition. Enter the standard candle. Imagine you are in a vast, dark field at night, and you see a familiar lantern you know intimately. If you know its true brightness, you can judge how far away it is by how dim it appears. Astronomers searched for cosmic lanterns, stars whose true brightness they could deduce from other properties. The breakthrough came with Cepheids variable stars. These are giant stars that pulsate rhythmically, growing brighter and dimmer over days or weeks. In the early 1900s, Henrietta Swan Leavitt discovered a beautiful and powerful relationship. The longer a Cepheid's pulsation period, the greater its true, intrinsic brightness. So, by simply measuring how long it takes the star to pulse, you know how bright it really is. Compare that to how bright it looks from Earth, and you have its distance. This was the master key that unlocked the universe's scale. Using Cepheids observed in fuzzy patches of light called nebulae, Edwin Hubble made a monumental discovery. Those nebulae were not clouds within our own Milky Way. They were entire other galaxies, islands of stars millions of light years away. The universe was suddenly, breathtakingly larger than anyone had dreamed. But even Cepheids have their limit. To measure distances to galaxies billions of light years away, we need an even brighter beacon. That beacon is a stellar explosion of such consistent fury, it becomes the ultimate standard candle, a Type Ia supernova. It occurs in a binary star system where a dense white dwarf star steals matter from its companion. When it reaches a very specific critical mass, it undergoes a runaway thermonuclear explosion. Because this critical mass is always the same, the explosion's peak brightness is always nearly identical. When we spot one of these supernovae in a distant galaxy, we know its true, staggering luminosity. Its apparent faintness then tells us the vast distance to its host galaxy. This is how we measured the expansion rate of the universe itself and made the mind-bending discovery that this expansion is accelerating, driven by a mysterious force we call dark energy. The cosmic distance ladder is a profound testament to the cumulative, bootstrapping nature of science. We start with a simple geometric step we can trust absolutely. That step calibrates the Cepheids. The Cepheids then calibrate the supernova. Each rung is secured by the precision of the one below it. There is no single leap to the edge of the observable universe, only a careful, interconnected chain of reasoning and measurement built over centuries, from the star catalogues of Hipparchus to the digital sensors of the Hubble Space Telescope. It shows that to comprehend the cosmos, we must build our understanding one careful, quantified step at a time. That common language for truth now flows through a global network of cables and servers. The invisible infrastructure of modern research is built on a simple, powerful agreement, the International System of Units. This is not just a set of definitions, it is a social contract among scientists worldwide. When a researcher in Tokyo publishes the melting point of a new compound, they report it in degrees Celsius. A team in Geneva reading that paper knows exactly what that number means without conversion or guesswork. This shared grammar allows for something miraculous, the aggregation of knowledge. Individual experiments, often small and specific, become data points in a vast collective dataset. Think of it like a global puzzle. A lab in California might measure how a new material reacts to heat. A separate team in Germany might test its electrical properties. A third group in Singapore studies its behavior under pressure. Because they all use the same fundamental units, their results can be combined, compared, and fed into powerful computer models. The resulting understanding of that material is far richer and arrives far faster than any single team could achieve alone. This network effect accelerates discovery at an exponential rate. It is the reason we can tackle challenges of planetary scale like climate change. Thousands of weather stations, ocean buoys, and satellites, operated by dozens of nations, collect petabytes of data on temperature, salinity, and carbon dioxide levels. Because this data is gathered using calibrated instruments and reported in standardized formats, it can be woven together to create a precise, dynamic model of our entire planet's climate system. Without this universal framework, we would have a cacophony of incompatible numbers, a Tower of Babel for data. The real innovation, then, lies not merely in the brilliance of a lone inventor, but in the humble, meticulous protocols that govern how we report what we find. The mandatory methods section in every scientific paper, detailing the equipment and procedures used, is a testament to this culture of verification. It allows anyone, anywhere, to attempt to reproduce the results, strengthening the collective finding. This framework of trust turns competition into collaboration. Rival labs might race to be first, but they run on the same track, using the same rules. Their findings either converge, reinforcing a new truth, or diverge, highlighting an error or a deeper mystery to be solved. The entire edifice of modern knowledge, from the confirmation of the Higgs boson to the mapping of the human genome, rests upon this unseen foundation of agreed-upon measurement. It is the quiet agreement that allows us to hear the universe's faintest signals above the noise of our individual uncertainties. But that global network of data finds its most extreme expression not in a server farm, but buried 100 meters beneath the French-Swiss border. The Large Hadron Collider is not merely a machine, it is a cathedral of measurement. Imagine a circular tunnel 27 kilometers long, a subterranean racetrack where protons are accelerated to 99.9999991% of the speed of light. Guided by thousands of superconducting magnets colder than the void of space, these particles are steered into head-on collisions of unimaginable energy. The purpose of this monumental engineering feat is breathtakingly simple: to measure the fleeting, chaotic debris that erupts from these microscopic fireballs. The machine itself is inert, a silent ring of steel and cable. It only comes alive to serve the detectors, the colossal digital cathedrals built at the collision points. Names like Atlas and CMS are not just acronyms, they are layered universes of sensors, each designed to capture a specific signature from the subatomic shrapnel. Silicon trackers map the paths of charged particles, calorimeters capture and measure their energy, muon detectors identify the most elusive penetrators. Every single component, from the smallest pixel to the largest magnet, exists for one reason: to transform an ephemeral event into a torrent of quantifiable data. This is the apex of measurement-driven science. The entire apparatus, a collaboration of thousands of scientists from over 100 countries, is a single, unified instrument for asking the universe a question. And in 2012, it delivered an answer. From the analysis of trillions of collisions, a subtle statistical bump emerged in the data, a consistent signal amidst the noise. This was the Higgs boson, a particle whose existence confirms the mechanism that gives all other particles their mass. The discovery was not a eureka, a moment of seeing something in a bubble chamber. It was the culmination of a global, meticulous process of measurement and statistical verification. The LHC demonstrates that at the very frontier of knowledge, the pursuit of a single measurement becomes a monumental sociological endeavor. It requires the standardization of petabytes of data, the calibration of millions of channels, and a shared language of analysis that transcends borders. This machine, built to probe the most basic rules of existence, stands as the ultimate testament to a simple truth: to understand what we are made of, we must first learn to count the pieces with absolute precision. And if we can build such a device to measure the fabric of spacetime, we have also learned to construct an entire fleet of instruments to take the vital signs of our own fragile world. High above the swirling clouds and the blue oceans, a silent sentinel keeps watch. It is the Gaia spacecraft, part of a vast orbital fleet, and its mission is to take the pulse of our living planet. These satellites do not see political borders or human cities, they see systems. With the unblinking eye of a spectrometer, they can detect the faint molecular signature of carbon dioxide in a column of air. A radar altimeter can measure the precise height of an Antarctic ice sheet to within a centimeter, tracking its heartbreaking thinning over decades. An infrared sensor maps sea surface temperatures, revealing the spreading blush of ocean heat waves. This is not merely observation, it is the continuous, quantitative measurement of Earth's vital signs on a global scale. For the first time in history, we have a consistent, planet-wide dataset that speaks in numbers, not anecdotes. We can now say with certainty that the average global temperature has risen by more than 1 degree Celsius since the late 19th century. We can measure the exact rate at which glaciers are retreating in meters per year. We can count the square kilometers of rainforest lost to fire or clearing each month. This data transforms our understanding. Ecology and climatology were once sciences of local weather stations and painstaking field surveys, limited by geography and time. Now they are predictive, global disciplines. Scientists can feed these torrents of satellite measurements into complex computer models, simulating the future of hurricane intensity, monsoon patterns, or sea level rise with a precision that was once pure science fiction. The evidence gathered from orbit has become the undeniable bedrock of international climate policy. When world leaders convene, they are not arguing over vague fears. They are negotiating over graphs and trend lines generated from this objective, space-based measurement. It proves that to solve a problem of planetary scale, we must first agree on how to measure it. This network of orbital instruments represents the ultimate application of our measurement genius, turning our most advanced technologies not outward toward the stars, but back upon our own fragile home. It gives us a mirror held at the distance of orbit, showing us the precise impact of our collective presence. And if we can measure the health of an entire planet from space, the logical next step is to turn that same quantifying gaze inward, toward the most complex system of all, the blueprint of life itself. The silent sentinels in space measure the health of a planet, but a quieter revolution was learning to read its most intimate instruction manual. The gene sequencer did not measure distance or mass, it measured meaning. Before its invention, biology was a science of observation, classifying the shapes of leaves or the patterns of inheritance. The fundamental code of life, deoxyribonucleic acid, was a locked book. Then came a series of breakthroughs that turned that book into a digital file. The automated DNA sequencer, emerging in the late 20th century, was not a single tool but a pipeline of precision. It used chemistry to copy and tag the 4 building blocks of DNA, adenine, thymine, cytosine, and guanine, then separated them by size. A laser would read the fluorescent tags as they passed by, translating the molecule's physical structure into a stream of letters A, T, C, and G. This was measurement redefined, not of a physical quantity, but of information itself. The sequencer transformed biology from a descriptive science into a quantitative, information-based one. Suddenly, the blueprint of an organism was not a mystery, it was data. This new capability made an impossible dream tangible, reading the entire human genome. The Human Genome Project became a global, decade-long measurement marathon. Laboratories around the world raced to sequence every one of the roughly 3 billion base pairs in our DNA. The completion of that first reference genome in 2003 was a milestone that echoed the first map of a new continent. It gave us a baseline, a shared text against which all variation could be measured. This is where the true power emerged in comparison. By sequencing the genomes of thousands of individuals, scientists could identify which tiny differences in that code were linked to specific health challenges or traits. This is the foundation of personalized medicine, where treatments can be tailored not just to an illness, but to a person's unique genetic makeup. On a grander scale, by comparing the genomes of different species, we gained a powerful new lens on evolution itself. We could now measure the genetic distance between a human and a chimpanzee, or trace the molecular changes that allowed a fish to walk on land. evolution was no longer just a story told by fossils. It was a documented history written in a common genetic language, with timestamps estimated by the rate of molecular change. The sequencer exemplifies a profound truth that innovations in measurement redefine what is knowable. It turned the complex analog blueprint of life into a digital code that could be analyzed, edited, and understood. We moved from observing life to reading its source code, and as we learned to decode the biological hardware of life, a far more elusive measurement beckons, the software of consciousness, the mind itself. The gene sequencer decoded the blueprint of life, but the mind remained the final uncharted territory. How do you measure a thought? For centuries, the inner world of consciousness, emotion, and decision was the exclusive domain of philosophers and poets, a realm of pure subjectivity. Then, a quiet revolution in the late 20th century gave us a new kind of lens. Technologies like functional magnetic resonance imaging, or fMRI, and electroencephalography, EEG, began to translate the silent symphony of the brain into visible, quantifiable data. An fMRI machine does not read your thoughts like words on a page. Instead, it detects the subtle, delayed rush of oxygen-rich blood to regions of the brain that have become more active. It creates a living, color-coded map of mental effort. When you solve a puzzle, a specific network lights up. When you hear a loved one's voice, another area glows. EEG takes a different approach, placing a net of sensors on the scalp to listen to the constant crackle of electrical communication between billions of neurons, translating their chatter into wavy lines on a screen. These are not photographs of ideas, but they are their signatures. For the first time, the subjective feeling of sadness, the flicker of a memory, or the moment of choosing between two options could be correlated with objective, physical changes in the brain. We began to quantify the unquantifiable. A neuroscientist can now present a volunteer with a moral dilemma and watch as the conflict plays out across the neural landscape, measuring the engagement of areas linked to emotion, reason, and social judgment. This is the new frontier, the measurement of consciousness itself. It is a field still in its thrilling infancy, where each new study refines our map of this 3-pound universe. Yet, with every new correlation discovered, a profound philosophical question grows louder. If our decisions, our loves, our very sense of self can be traced to patterns of blood flow and electrical sparks, what does that say about free will? Are we merely observing the mechanical output of a biological computer? This tension is not a flaw in the science, but its most important revelation. Every new domain we learn to measure, from the heavens to the atom, has ultimately challenged our deepest assumptions about our place in the cosmos. Mapping the mind forces us to confront the possibility that the thinker is also a thing that can be measured. The journey from using our own foot to measure a field to using magnetic fields to measure a daydream illustrates the relentless, breathtaking expansion of our quantitative grasp on reality. We have moved from measuring the world around us to measuring the world within us. This brings our story to a final, elegant case study, a historical mystery that was solved not by a dramatic dig, but by the most meticulous measurement imaginable. For over a century, the ultimate arbiter of mass on our planet was a small, shiny cylinder, locked away in a vault at the International Bureau of Weights and Measures near Paris. It was known simply as Le Grande K, the International Prototype Kilogram. Crafted in the 1880s from a platinum-iridium alloy chosen for its stability, it was the physical embodiment of the kilogram. Every scale on Earth, from a grocer's balance to a pharmaceutical microbalance, was ultimately calibrated against copies of this one perfect artifact. It represented the peak of the old philosophy that measurement required a tangible master object, but this system contained a hidden, profound flaw. The object was in the world, and the world changes things. In the early 2000s, during a rare ceremonial cleaning and comparison with its official copies, scientists made a startling discovery. The master kilogram had lost mass, not much, only about 50 micrograms, roughly the weight of a single grain of fine sand. But in a world built on nanoscale precision, this was a seismic event. The perfect standard was imperfect, it was drifting, the implications were staggering. If the definition of the kilogram was tied to a physical object that could change, then the kilogram itself was changing. The mass of the universe, as measured by humanity, was subtly shifting because a speck of dust had perhaps adhered to a vaulted cylinder in France, or because atoms had slowly escaped its surface over a century. This was the ultimate vulnerability of an artifact-based system. It meant our most fundamental constants, the numbers we use to describe reality, were anchored to a speck of matter subject to the very erosion it was meant to transcend. The quest for a perfect standard demanded a final, radical leap. We had to abandon the object entirely and anchor our units not in a thing, but in an idea, in a truth so fundamental it was woven into the fabric of the cosmos. The solution came from the quantum realm. After decades of painstaking experiments, metrologists achieved the impossible. They measured the Planck constant with exquisite accuracy. This is a fundamental number from quantum mechanics that relates the energy of a photon to its frequency. It is a fixed value, a true constant of nature, presumably the same everywhere in the universe and for all time. The elegant breakthrough was to use this constant to define the kilogram through a device called a Kibble balance, which essentially weighs mass against an electromagnetic force calibrated with the Planck constant. On May 20, 2019, the kilogram was officially redefined. No longer was it the mass of a cylinder in Paris. A kilogram is now defined by fixing the numerical value of the Planck constant. The artifact was retired, its mission complete. This was not merely a technical update, it was a philosophical culmination. It marks the final step in a journey that began with a human foot in the mud. We have moved from the personal to the royal to the planetary and now to the universal. Our standards are no longer things we make, but truths we discover. They are secured in the immutable laws of physics, accessible to any civilization with the knowledge to decode them. This redefinition ushers in a new and remarkable era, one where our ability to measure is limited only by our ingenuity and never again by the imperfections of a physical object. The kilogram was set free from its Parisian vault, but it was just one piece of a much larger, silent revolution. In that same year of 2019, the entire foundation of our measurement system was quietly rewritten. The International System of Units, the C, underwent a historic overhaul, redefining all 7 of its base units in a single, breathtaking sweep. The meter, the second, the kilogram, the ampere for electric current, the Kelvin for temperature, the mole for chemical amount, and the candela for light intensity. Each one was now anchored not to a physical artifact or a local phenomenon, but to a set of universal constants. The speed of light in a vacuum, a fixed 299,792,458 meters per second, defines the meter. The unchangeable oscillation of a cesium atom defines the second. The Planck constant, a tiny number from quantum theory, defines the kilogram. The charge of a single electron defines the ampere. These numbers are not human inventions, they are cosmic settings woven into the very structure of reality. Think of it this way, for centuries we built our rulers by carefully copying a king's scepter. Now we have learned to read the ruler that was built into the universe at the moment of its creation. This is a system designed for eternity and perhaps for other minds. Any intelligent civilization anywhere in the cosmos could theoretically derive the same set of constants from observing nature. Our units of measurement have become a potential universal language, decipherable by anyone who understands the laws of physics. This represents the ultimate triumph of a scientific ideal first glimpsed by those French revolutionaries who measured the Earth. It is a framework derived purely from nature's own laws, ensuring a stability and universality that no physical object could ever provide. It means the ruler we use to measure a new material in a lab today will be identical to the ruler used by scientists 1,000 years from now, or 1,000,000 light years away. With this perfect, immutable framework now in place, we are not at the end of a story, but at the beginning of a new chapter. Freed from the drift of artifacts and the limitations of our planet, what new, deeper mysteries of the cosmos can we finally begin to solve? Our perfect, universal system of measurement now faces its greatest challenge, the dark side of the cosmos. The discoveries of dark matter and dark energy are not triumphs of direct observation, but profound puzzles born from measurement. We cannot see them, touch them, or trap them in a detector. We know they exist only because our most precise measurements of the universe reveal a glaring discrepancy. When astronomers measure how fast stars orbit the center of a galaxy, they find the outer stars moving far too quickly. According to the laws of gravity, based on all the visible stars and gas we can count, those distant stars should be flung into the void. Something unseen, something that does not interact with light, must be providing the extra gravitational glue to hold the galaxy together. We call that something dark matter. Similarly, when we use our cosmic distance ladder to measure the expansion of the universe, we find it is not slowing down as expected from the gravitational pull of all matter. It is accelerating as if an invisible force is pushing space itself apart. We call that dark energy. These are not minor errors. Dark matter appears to make up about 27% of the cosmos, and dark energy a staggering 68%. The ordinary matter we see and are made of, the stuff of stars, planets, and people, accounts for less than 5% of everything. This means our current instruments, as magnificent as they are blind to 95% of reality. Solving these mysteries will demand a revolution not just in theory, but in our very ability to measure. We need new eyes. The emerging field of gravitational wave astronomy provides one such sense. When massive objects like black holes collide, they ripple the fabric of spacetime itself. Detectors like LIGO and Virgo can now measure these ripples, vibrations smaller than the width of an atomic nucleus. This allows us to listen to the dark universe in a way telescopes cannot see it. Next-generation particle detectors buried deep underground are waiting for a hypothetical dark matter particle to bump into an atom of xenon or argon, a direct measurement that would change everything. These frontiers remind us that measurement is never a solved problem. It is an eternal conversation with the unknown. Every stubborn anomaly in our data, every gap between prediction and observation, is not a failure. It is a signal, a whisper pointing to the next limitation in our tools. The quest to measure the dark universe is the current, thrilling chapter in humanity's oldest story. It proves that our desire to quantify reality is the engine of discovery itself, constantly pushing us to build better questions in search of deeper truths. And this relentless drive to measure with ever greater precision does not just reshape our understanding of the cosmos. It fundamentally transforms the society we build here on Earth. Yet this incredible power to measure carries a profound and often overlooked responsibility. The same tools that reveal the cosmos can also be used to confine the human spirit. For measurement is not a neutral act, it is an act of definition. When we choose what to count and how to count it, we are making a statement about what we value and what we choose to ignore. This power to quantify can easily become a power to control and categorize in ways that flatten the beautiful complexity of human experience. Consider the intelligence quotient test, originally developed as a practical tool to identify children who needed educational support. Over time, this single numerical score was misapplied as a definitive measure of a person's worth and potential, leading to policies that reinforced social divisions and limited opportunities based on a dangerously narrow metric. A human mind, with its creativity, empathy, and resilience, cannot be captured by a three-digit number. Today, we see similar dynamics in digital scoring systems that attempt to rate trustworthiness or social behavior, reducing the nuanced story of a life to a simplistic ranking. These systems risk creating new forms of exclusion, where algorithms make consequential decisions based on data that may be incomplete, biased, or simply incapable of capturing context. The ethical weight of measurement grows heavier with its precision. This dilemma is not just social, it is woven into the fabric of physical reality itself. In the quantum realm, scientists made a startling discovery. The very act of measuring a system fundamentally changes it. You cannot observe a subatomic particle without interacting with it, without disturbing its state. This principle, called the observer effect, is a profound metaphor for all measurement. Our gaze is never passive, our tools are never invisible. When we measure a forest only for its board feet of timber, we risk missing its role as an ecosystem. When we measure a student only by standardized test scores, we risk overlooking their unique talents. The tool shapes what we see, and in seeing it, we change it. This means that with every advance in our ability to quantify the world, we must also advance our wisdom in asking why we are measuring and for whose benefit. The history we have traced is not a simple march of progress, it is also a cautionary tale. The same imperial systems that built global trade were also tools of colonial administration. The demographic surveys that can help allocate public resources can, in the wrong hands, be used for oppression. This is the double-edged sword. Measurement gives us clarity and control, but without ethical guardrails, it can lead to dehumanization and a loss of mystery. Our responsibility, then, is to cultivate measurement with humility. We must design systems that acknowledge uncertainty, that preserve privacy, and that leave room for the unquantifiable, for intuition, for art, for the sheer wonder of things that cannot be pinned down by a number. The goal is not to stop measuring, but to remember that the map is not the territory, the data point is not the person, the model is not the living, breathing world. As we stand at the threshold of measuring our own consciousness and programming artificial intelligences that will measure us in return, this ethical dimension becomes the most important frontier of all. The ultimate test of our civilization may not be how precisely we can measure the universe, but whether we can do so with a deep and abiding respect for all that our numbers will never fully explain. This journey reveals a profound truth, that measurement is far more than a collection of tools. It is the very grammar of scientific thought itself. It is the language we invented to ask nature questions and to understand its replies. From pacing out a field with our own footsteps to defining a second by the unwavering vibration of a cesium atom, each leap in our ability to measure has directly expanded the horizon of the knowable. What was once a mysterious force, like gravity or electricity, became a manageable law the moment we learned to give it a number. These innovations built the foundations of modern science by providing something indispensable, a common, quantifiable ground. On that shared ground, a theory proposed in Berlin can be tested in Tokyo. A discovery made in a quiet shed can be verified across an ocean. It transforms personal insight into public truth, allowing human knowledge to accumulate, brick by precise brick, across generations and continents. Today, our standards are no longer locked in vaults but are secured in the constants of the universe, a perfect framework for a future of limitless discovery. We carry forward this incredible legacy, a story not of cold calculation, but of burning curiosity and relentless precision. It reminds us that every great discovery in our past, and every one yet to come, begins with a deceptively simple question. How can we measure that so the next time you glance at an ordinary clock or use a simple ruler, see it for what it truly is, a fragment of that grand story, a key that has unlocked a deeper layer of reality? I would love to hear what measurement captures your imagination the most. Share your thoughts in the comments below, and thank you for exploring this foundational history with me.